So this workshop is applications of the Fundamental Theorem of Arithmetic. I have to say, this is a bit of an ugly statement of the Fundamental Theorem of Arithmetic. I'm thinking of simplifying it for next year. Just wanted to be very careful about it, right? But okay, for every integer that's greater or equal to 2 can be written in essentially a unique way as a product of powers of prime numbers. But I put some, to try and make it relatively unique, we say the prime numbers are different, so P1 up to Pm have to be different, but the powers can be the same as each other if they want. So K1, K2 up to Km, they're just any old positive integers. We don't know what they are, so there might be several 2's in there and a 3 and a 7. Who knows what powers they're being raised to, okay? But all we're doing is something that you probably did at school a long way back, looking what power of 2 divides a number, if there are any 2's, take as many 2's out as possible, then see if there's any 3's, take as many powers of 3 out as possible, then see if there's any 5's, and so on, and that way decompose it as a product of prime powers. And it's unique except you can change the order. M equals 1, that's the case when there's just one prime involved, and so it's a power of a prime number. M equals 0 is that strange case that I mentioned before when you don't multiply any powers together and you get 1. I was saying n should be greater or equal to 2, so I wasn't allowing that. Right, so we'll call these the standard assumptions on these numbers, just so we don't have to write all these conditions down all the time. So if I say n is this product of powers of primes like this, in the usual way, it means that the prime numbers are different, but the powers don't have to be. So now your first task, and this is like a question we did in lectures, is to find out how many different positive integers there are that are divisors or factors of 540. So we did one of these in lectures. Let's see if you can remember how we did it. And I've zeroed the voting, so you can vote on this when you like. We'll come round and see if you know how to do this one. $29 votes so far. Okay, let's see what people have gone for. 30 votes with a majority for B. Which is correct. Okay, you start, so how do you do it? You have to find the prime factorization, which we know is essentially unique. And according to my notes, it turned out that 540 is equal to 3 cubed times 2 squared times 5 to the 1. In any order you like, it doesn't matter, okay? So hopefully you know how to find this prime factorization by now. If you don't know how to find the prime factorization, I suggest you come and ask me or ask a friend. So I'm going to assume that you know how to find the prime factorization of a number. But if you don't, you should find out. Okay? And then you have to figure out what are the factors. So the positive factors are 3 to the I times 2 to the j times 5 to the k, where I is only allowed to be 0, 1, 2, or 3. So I is 0, 1, 2, or 3. That's 4 possibilities. J is in 0, 1, or 2. That's 3 possibilities. And K is 0 or 1. If you take them all to be 0, then you get 3 to the 0 times 2 to the 0 times 1 times 5 to the 0, which is 1, which is a perfectly good factor. If you take I to be 3, as big as possible, and j to be 2, and k to be 1, then you get 540, which is also a positive factor of 140. If you choose any other numbers for I, j, and k, you get something in between. Number of possibilities, then, 4 times 3 times 2, because you can make these decisions independently. 4 times 3 times 2 is 24. And as an exercise, you can systematically list them all, but don't do that now, okay? So you can go away and write down all 24 factors of 540 using this system. Let's do this in the abstract. Oh no, we'll do that in a minute. Okay. So now I want you to think about the following. This is a lot of questions about equivalencies, right? So which of the following statements are true for all natural numbers? 15 divides n if and only if 3 divides n and 5 divides n. One direction is obvious, the other direction you have to think about. 24 divides n if and only if 4 divides n and 6 divides n. One way might be easier than the other. 45 divides n if and only if 5 divides n and 9 divides n. Okay, so your task is to figure out how many of these statements are true, how many of these statements are false. Well, the question is how many are true. So let me zero the votes again, and you can start thinking about that. And you can base your answer on thinking about prime factorizations again. Okay, so you can vote whenever you like. I shall pause the recording. Okay, I've restarted the recording. The responses this time appear to be a bit random. So let me say something about this. Okay, now all of the forward implications are all true. Okay, so the forward implications are all true. But there's a problem with one of the backward ones. So the first one and the third one are actually true, and the second one is false. It's the backwards implication that's false. Okay? So the correct answer is that 2 of these statements are correct. Now, let's see if I can persuade you of this. Right? So the first thing is, the forward implications I will take as fairly obvious, because we already know that if a big number divides something and something else divides, because 3 divides into 15, if 15 divides into n, then 3 would divide into n2. This is something we actually showed in a previous class. So the forward implications are all easy. If a number goes into n, then anything that goes into that number will go into n as well. We actually proved that in the abstract before. So it is true that 24 divides n implies 4 goes into n and 6 goes into n. Because one way to see that, for example, is n over 4 is equal to n over 24 times 24 over 4, which is equal to n over 24 times 6. So if n over 24 is an integer, then n over 24 times 6 is still an integer. So that's one way of seeing it, among many others. Okay. So that shows that if 24 goes into n, then so does 4, and of course so does 6. But the reverse is false. Okay. The converse is false. So who's got a counterexample that shows that it's wrong coming back? You've got 12, yes, okay. So the reverse implication is wrong. For example, 4 divides 12 and 6 divides 12, but 24 does not divide 12. So that's a counterexample, shows that it's possible for 4 to divide n and 6 to divide n without 24 dividing n. Okay? Now, 1 and 3 are rather similar, though perhaps 1 is easier than 3. But, again, the forward implication is easy. If n is divisible by 45, then of course it's divisible by both 5 and 9. But the other way around is less obvious. So why is it that if n is divisible by 5 and n is divisible by 9, that n has to be divisible by 45? Well, the answer is, we look at the prime factorisation of n, and note that 9 is equal to 3 squared. That's 9 equals 3 squared. Now, so suppose 5 divides n and 9 divides n. What does the prime factorisation of n look like? I notice that n is definitely greater or equal to 2, because n's actually got to be at least 9 at this point. Okay? So, what is the prime factorisation of n? Well, we don't know, of course. But whatever the prime factorisation of n is, it does include 5 and 3 squared at least. Okay? So it's definitely got a 5 in, it's definitely got a 3 in, and we're going to need 3 squared at least to get it divisible by 9. So we must have n equals 5 to the I times 3 to the j times some other stuff, which could be 1. The other stuff, there might not be any other primes in n. Okay, so this other stuff might be 1. But it's definitely got a 5 in, it's definitely got a 3 in. Moreover, obviously I is at least 1, but j has to be at least 2, or you can't get 9 to divide into n. So with I greater or equal to 1, since 5 goes into n, and j greater or equal to 2, since 3 squared goes into n. You can't get, you see, when you write down the prime factorisation of n, you can immediately see what's the biggest possible power of each prime that goes into it. And in this case, it's going to be, you'll get I for the 5 and j for the 3, and there could be some other primes raised to other powers, or there might not be any others. Okay? But in particular, 45 already goes into 5 to the I times 3 to the j. Will go into 5 to the I times 3 to the j already. Remembering that I is at least 1 and j is at least 2, so you get 45 times something. So certainly 45 goes into n. Because n is some integer times 5 to the I times 3 to the j. So that's how you do it. So the idea is you think, what's the prime factorization of n look like? How many powers, what power of 3 is going to go into it? What power of 5 is going to go into it? And we've got at least 5 to the 1. We've got at least 3 to the 2. And one of the things you do is you start looking at what's the highest power of each prime that goes into your integer, and you start working with that. So that's how you get 45 divides n whenever 5 divides n and 9 divides n. Any questions about that argument? So implicitly here, this is the prime factorization of n. This is in the usual way. There may be some other prime factors. We don't care because you're home already. Okay, so assuming you believe that one, let's move on to something more abstract. So let's find a formula for the number of positive factors of an integer n. Okay? So n will be n is going to be a positive integer that's at least 2. We'll write it as a product of prime powers like the Fundamental Theorem of Arithmetic. So here it is, p1 to the k1, p2 to the k2, and so on, pm to the km, in the usual way. So these prime numbers are different. The powers, k1 up to k2 up to km, are natural numbers that don't have to be different from each other. But the primes are different. And we could use product notation, which you should have come across by now. It turned up in the week 2 questions. If you haven't met it anywhere else, this we added in lectures as well. This means, this is just another way of writing the same thing. Multiply together p1 to the k1 times p2 to the k2 and so on, multiplied by pm to the km. It's like a sum, except you do it by multiplying instead. And now you can list all the natural numbers. And the question is, how many different positive factors does n have? So let me make sure I get 0 the votes. Okay, I've deleted all the responses. Your task, I'll give you a little bit of time to think about this. It should fit with what we did before. And your options are to add the powers, to multiply the powers, to multiply one more than the powers, or to take n factorial, which is n times n minus 1 times n minus 2 and so on, or any of the other options. Okay, let's see if you can fit the formula to your previous calculation. If you haven't voted yet, then it's your last chance. Okay, so majority in favour of C, which is correct. Let me not go through that in detail. Let me just try and compare that with what we did before for 540. So the claim is that you look at the powers involved, you add 1 to each power, and you multiply all those numbers together. Let's just see if that fits with what we did for 540. So we'll just go back to 540. 540, we said it was 3 cubed times 2 squared times 5 to the 1. Now, because it was 3 cubed, there were 4 possibilities for what power of 3 to take. And because it was 2 squared, there were 3 possibilities for the power of 2 we could take, because you're allowed to take power 0. And because it was 5 to the 1, there were 2 possible powers of 5 we could take, 0 or 1. So we ended up by taking 4 possibilities there, 3 possibilities there, 2 possibilities there, and we did 4 times 3 times 2 to get 24. So what you have to do is you look at all the power, you look at those powers involved, or rather the indices, you add 1 to them, and you multiply together. And that is formula C. And you can convince yourself that this really is right with a more abstract proof, if you like. But I won't say more about it than that. It fits with what we did before, and this is the abstract proof. OK, now, I want to tell you something about highest powers. So you take a natural number, and you take a prime number, and you note that p to the naught equals 1. OK? And now you ask, what's the biggest k could be so that p to the k divides n? And that might be naught. OK? If n is not divisible by p, then the best you can do when you're using p is to take p to the naught, because 1 will divide into n. OK? On the other hand, if p does divide n, then you've got p to the 1 dividing n, and you can ask, does p squared divide n? If it does, you can ask, does p cubed divide n? Obviously, you get stuck eventually, because you'll get much bigger than n if you go to big powers of p. So there's a limit to what power of p divides n, and in fact, you can read it off from the prime factorization. So when you do your unique prime factorization of n, assuming if n is divisible by p, then p has to be one of these primes. We know that if you take a product of sort of alien primes, it's not going to suddenly be divisible by some completely different prime. The only primes that divide n here will be p1, p to pm. And the highest power of p1 dividing n is k1. The highest power of p2 dividing n is k2, and so on. Terminology issue here. When we talk about the highest power of p dividing n, we mean the index. Though that's arguable, but that's what most people do. So we'll stick to that version of it. The highest power of p dividing n is the biggest index you can have, so that p to the k divides n. So when you write the prime factorization, you can read off the highest powers. And for any other prime that isn't in the list, the highest power of that prime dividing n is 0. Now, I note that if you look at this, if you suppose you did n squared, is p1 to the 2k1, p2 to the 2k2, pm to the 2km, and you will note that the highest power of p1 dividing n squared has doubled. It was k1, and now it's 2k1. And the same for any other prime dividing n. And also the same for any prime that didn't divide n. Because if a prime didn't divide n, it doesn't divide n squared either. Yes?
Why isn't it p2?
It's supposed to be 2k2. I've just written it wrong. Thank you. Have I written? I don't know what I've written there. But what I wanted to write was 2k2. Thank you. So for the primes that do divide n, the highest power is doubled. And for the primes that don't divide n, they still don't divide n squared either. And so the highest power still doubled, because it was naught and it's now naught, which is twice naught. So it's OK. You still double the highest power, even if you didn't divide the number. So here's your question. Let n be a natural number. Let p be a prime number. And suppose that k is the highest power of p dividing n. What is the highest power of p dividing p squared n cubed? And here are some plausible possibilities for you to think about. And if you sort this one out, you can move on to question 6. We'll come round and see how you're getting on with those. Okay, so since we're pretty much out of time, I'll just say a little bit about this to finish. So let's let K be the highest power of 7 dividing M. And let L be the highest power of K, the highest power of 7 dividing N. Then for M to the 5th, so the left-hand side is M to the 5th. The highest power of 7 dividing M to the 5th is going to be 5K. For the right-hand side, so for n to the 5th, the highest power of 7 would be 5L. But because it's 7 cubed times n to the 5th, it's going to be 5L plus 3. Five L plus 3, okay? But we're assuming at the moment that m to the 5th is equal to the 7 cubed n to the 5th, which means that they should have the same highest power of 7. We need 5k equals 5L plus 3. But that's impossible. If you work modulo 5, for example, they don't have the same remainder. Left-hand side is divisible by 5 and the right-hand side isn't. You've got remainder 3. So I would say but 5k is congruent to 0 mod 5, and 5l plus 3 is congruent to 3 mod 5. Different remainders, they're not equal for sure. Lots of other ways to do this bit. So this time we're working mod 5. So 5k is not equal to 5l plus 5. That's a 5l plus 3. That's a contradiction, because the powers of 7 were supposed to be the same. So we have m to the 5th is not equal to 7 cubed times n to the 5th. And I leave the rest of the exercise that you can now prove that 7 to the power 3/5 is irrational. Okay.